but it's something 1,500 or 2,000. Millions and millions of dollars just doing the material science on those shuttle tiles. And they were remarkable pieces of, I remember actually seeing, I think the demonstration was in our book. And he did for about a week, up to about 2,500 kelvins. I don't know. They reached with the tongs, pulled it out, and almost instantly the edges and the corners went black, and the rest of it continued to glow. Can you explain why the edges and the corners went black? 3 alpha delta t. Yes, when it's a two-dimensional problem, it's 2 alpha. When it's a one-dimensional problem, it's 1 alpha. When it's a three-dimensional problem, I'd like you to show that 3 alpha is an adequate argument. I'd like you to do what we just did, only do it in 3 dimensions. You're going to find a little corner that you would throw away for exactly the same reason. You might even anticipate, I'm sure you have anticipated, that the part that you're going to throw away is going to have an alpha cubed. If alpha squared is small enough to be neglected, alpha cubed must be really small. So I'd like you to do it, but I'd like you to do a formal argument just like we did here to demonstrate that, to a good approximation, delta A can be approximated as A naught twice alpha delta t, and delta B can be approximated as V naught alpha delta, 3 alpha delta t. Okay? And our book, by the way, says that 3 alpha is often called beta. And we just won't use the beta. Except in the case of, guess what, a liquid. We'll use beta to represent the coefficient of volume expansion of a liquid. Okay? Well, ladies and gentlemen, that's all there is to chapter 20. In calorimetry and expansion, we do talk a little bit about thermometers. Who invented the first practical thermometer? Do any of you know? Fahrenheit. Fahrenheit was the first one to come up with a thermometer like a modern thermometer. But there was someone who predated Fahrenheit who came up with a practical thermometer. I always find this interesting. It was Galileo. Galileo made the first real practical thermometer. Isn't that interesting? Now, we were talking about the heat transfer on shuttle tiles. I would now like to ask you, what are the forms of heat transfer? I want to name them, and I think probably the easy way to do it is to imagine an experiment. Let's imagine this experiment. I've got a hot fire burning right there, and I've got a long metal rod, here's my long metal rod. Well, it's not a metal rod, but pretend like it is. I have a long metal rod like this, and I'm holding one end of the metal rod in the fire, and I'm lecturing to you, okay, for a while. It won't be long, will it? Because while I'm holding this metal rod in the fire like that, what's going to happen? It's too hot, I'm not going to be able to hold it, huh? Okay? Obviously, heat is going to move up the metal rod. What is the name of that form of heat transfer? Correct. Please put in your notes exactly these words. Conduction is the movement of heat through a material medium. It's a very broad definition, but I hope you to put in your notes using exactly those words. Conduction is movement of heat through a material medium. And then open a parenthesis and write the word solid. Close the parenthesis. Now, I do hasten to point out, ladies and gentlemen, that you don't have to have a solid to have conduction. The reason I asked you to put that word in parentheses, it's just a reminder that when you use the word conduction, nothing is moving except the heat. Only the heat moves when you use the word conduction. So I put the word solid because in a solid nothing moves except heat itself. Compare that to this form of heat transfer. What if I went down to the glass blowing shop? Which, by the way, is a really fun class. I don't think they offer it here, do they? Glass blowing?
Probably not anymore.
The university I went to, at least as an undergrad, they had it as a chemistry class. You could make your own chemistry equipment. If you get into a school that has that class, take the class. It's fun and very useful. So we go down to the glass blowing shop and we have a glass tube made like this. We fill it to this level with water, just ordinary old water. Then I very carefully squirt dye into the water. Now this is interesting dye because it has it's neutrally buoyant. It has the same density as water. So when I very carefully squirt it right there, it goes in there and just sits there. It just stays there because it has the same density of water. That is until I bring the Bunsen burner right over here. See the Bunsen burner? Now I know this Bunsen burner looks an awful lot like a candle. That's because I draw candles better than I do Bunsen burners. But I bring the source of heat over there. And of course you know what happens. Just as soon as the heat gets there, I would see this dye start to move, wouldn't it? The dye would start moving like this, indicating that there is a circulation of the water caused by this heat. Can anybody explain why? Several of you are saying it, and I think you're saying it correctly with slightly different words. Were you saying this? I think I heard this. That the water here is warmed and therefore expands.
Yes.
Because of its expansion, it is buoyed up. Notice I didn't say warm water rises. A lot of people say hot air rises, right? If that's true, then all my lectures are right up there, aren't they? To say that warm water rises or to say warm air rises implies that it has a will. It doesn't have a will. The key word is buoyant. When I say that the warm water is buoyed up, what I'm saying is that the water expands because it's warm and therefore has lower density than the water around it. It therefore enjoys that buoyant force. You talked about the buoyant force in physics forward, did you? No. Well, there's a force equivalent to the expansion of the material times the weight of the material displaced. That's called the buoyant force. So that's a technical detail, that the warm water expands and is then buoyed up to be replaced by cool water, which will be heated and expand and will create a circulation. In so doing, the warm water moves up the column, and we have once again moved heat, haven't we? Only this time, it's obviously not conduction. Because this time, you warm a material, and then you move the warmed material. That's not conduction. Because in conduction, nothing moves but the heat. This is a second type of heat transfer. What's its name? This is convection. Let's use exactly these words, please. Convection is the movement of heat by moving a hot material medium. I'll say it again. Convection is the movement of heat by moving a hot material medium.